So this is COS 505. We're going to look into Chapter 2, data representation in computer systems. So this time around, I didn't write. I'm using the book lectures. So there may be some more information we can look over. Let me see. Let's go on to the objectives. Sorry about that. I just need to make some adjustments to the screen. We're going to understand the fundamental of numerical data representation and manipulation in digital computers. Master the skill of converting between various radix systems. Understand how error can occur in computation because of overflow and truncation. Understand the fundamental concept of floating point representation. Gain familiarity with most popular characters, codes. Understand the concept of error detecting and correcting codes. So we know what the most basic bit is basically on and off. And then the byte is a group of 8 bits. Word as a group of bytes, so it's 16, 32, or 64 is the most common. Group of 4 bits is called a nibble. So bytes store numbers using the position of each bit to represent a power of 2. So base of 2. So our decimal system is base 10. So here you can see the decimal number 947 in power of 10. You can see that. So the decimal number of 5836.7 in power of 10 is this, and so forth. So you can work through some of these examples. So the binary, we know binary is 0s and 1s. So you can see how this is converted to base 10. So 1 times 2 raised to the 4. So this is position 0, 1, 2, 3, 4, and so forth, how it's converted. So this is converting 190 to base 3. It's divided. And this way you go from the bottom to the top, and you say it's base 3. So there's some good examples you can look through. This lecture slides, I'm not going to cover every single example, but you can look through how these conversions are done, converting between bases, and you see how which way they go after they convert. So the binary numbering system is the most important radix system for digital computers. So it is, it is difficult to read long strings of binary numbers. So you can see that, it is difficult to read long strings of binary numbers. So you can see how they're broken up into binary, 4 bits. They're broken up into, then there's hex, then there's octal numbers. So you can see they're in multiples by 4. You can see they're also using color coding, so it's easier to read. So the conversions that we've looked at so far represented have involved only unsigned numbers. So to represent signed integers, computer system allocate the high order bits to indicate the sign of number. So leftmost bit. So this is called the most significant bit. So 0 is used to indicate positive number. 1 is used to indicate negative number. So the remaining bit contains a value. So this is the first bit, whether the number is positive or negative. So 3 ways in which signed binary integers may be expressed: signed magnitude, 1 complement, 2's complement. So in an 8-bit word, signed magnitude represents places the absolute value of the number in 7 bits to the right of the sign. So here's an example of an 8-bit signed magnitude. So this is +3 and -3. So this gets into more of the binary additions, how it's done. So you can take a look at these examples. Then we get into kind of additions, convert 75 and 46 to binary and arrange as a sum, but separate the positive sign bit from the magnitude bits. So sign magnitude representation is easy for people to understand, but it requires complicated computer hardware. So another disadvantage of the sign magnitudes is that it allows 2 different representation for 0, +0 and -0. So computer system employ a complement system for numeric value representation. So negative values represented by some numbers between a number and its base. So we've got the diminished radix. So you can see that notation. So the binary system gives us 1's complement. So remember, negative values are indicated by 1, the higher order bit. So here, this is indicated by 1. So remember to carry the bit. So that's carried over. So you've got this 2's complement. So although the n carry adds some complexity, 1 complement is simpler to implement than sign magnitude. So it still has a disadvantage of having 2 different representations, 0 and -0. So 2's complement solves this problem. So this goes through the signed integer representation. So this one, with 2's complement arithmetic, all we do is add 2 binary numbers, just discard any carries omitting the high order bit. So the carry is discarded in this case. So we run into issues of our calculations becoming too large. So this gets into more of the overflow. So this gives an example of overflow. So when the carry in and carry out of the sign bit differs, overflow happens. If the carry into the sign bit equals the carry out of the sign bit, no overflow has occurred. So this gets more into the floating point representation of the sign magnitude of 1's complement and 2's complement. So without modification, these formats are not useful in science or business applications. So we've got specialized hardware in today's computation that perform floating point arithmetic, but it doesn't require any kind of special programming. Some examples, getting into here. So computers use a form of scientific notations. So numbers written in scientific notations have 3 components. So you got the plus sign, mantesia, and the exponent. So computer representation of a floating point number consists of 3 fixed size fields. So you got the sign field, You got the exponent field and the significant field. So this is the simple model. So you got the floating point number is a 14-bit in length, 14-bit. I meant this one, significant. The sign, 14-bit. Exponent is 5-bit. The significant field is an 8-bit right there. So it's in order 14, 5, and 8. Some examples of how it's representative. You can take a look at those. And then the IEEE standards. So IEEE has a different standard for their single precision and double precision. So more into the IEEE standard and how it's representative. You can take a look at those. Character codes. Calculations are not useful until the results can be displayed in a manner that is meaningful to folks. So we also need to store the results of calculations. So human understandable characters have to be converted from computer understandable bits and patterns. So we got to convert these into where humans can understand. So different kinds of character codes. EBCDIC is one of the first widely used computer codes that support upper and lowercase alphabet characters. So you've heard of ASCII as a 7-bit, so American Standard Code for Information Interchange. Then there's other standards as well, and IBM mainframe standards that were used. So 16-bit system, the Java programming language and some other operating systems use Unicode. Character codes, different alphabet symbols, CJK, Han, user-defined. Error detection, so Hammond codes are codes word performed by adding redundant check bits or parity bits to data words. So it goes more into that as well here. It goes more into that here as well. So here it gives an example. You can look through those examples as well. Goes more into the examples. You can look through these examples using the Hamming algorithm. And more examples are shown here. So, conclusion, computers store data in the form of bits, bytes, and words using the binary number system. So computers do not speak the same language as we do. Hexadecimal numbers are formed using 4 bits, group called nibbles. Signed integers can be stored in 1's complement, 2's complement, or signed magnitude representation. Floating point numbers are usually coded using the IEEE 754 floating point standard. So floating point operations are not necessarily computative or distributed. Character data is stored using ASCII, EBCDIC, or Unicode. Error detection and correction codes are necessary because we can expect no transition or storage medium to be perfect. So CRC, Reed, Solomon, and Hamming codes are 3 important error control codes. So please review your lecture notes and also take a look at the chapter. Let me know if you have any questions. Thank you.